So we're going to be talking about a way of computing a limit that's very popular with students because it's it's a very nice rule. The rule is actually called L'Hopital's rule. Uh, Lots of different ways to spell the guy's name. Uh, one book, one popular book, spells it as with a small case L, and then it looks like hospital. L'Hopital's rule, and then art book has capital L with accented symbol here, so that's L'Hopital that way. Okay, in any event, if you do go looking it up on the internet, don't be surprised if you see 100 different ways of spelling L'Hopital's name. Okay, so we're going to be taking a look at a very popular limit, and that is we're going to take the limit as x approaches a of f of x divided by g of x, and we're going to assume that we get the ever popular 0 divided by 0, right? That is an indeterminate form, right? Because this indicates that we have to do more work, right, to try to figure out what the value is. Or, maybe I should say plus or minus infinity divided by plus or minus infinity. So L'Hopital's rule will work in this case too. Okay, so in these cases then we can compute the limit as x approaches a. By the way, the a could also be infinity, of f of x divided by g of x as the limit as x approaches a of f prime of x divided by g prime of x. And this is true provided that this limit exists or is plus or minus infinity. Okay. This is kind of an interesting little disclaimer here. So L'Hopital's rule works a lot of the time, but you do have to be careful of if the limit that you're computing does not exist, okay? Because then you have to backtrack and look at the original expression to see what happened. Okay, our book, by the way, gets away with this, or gets around this by saying that the g prime of a is not equal to 0, but that's not something that's usually required. Okay, so let's just take a look at a few examples. Suppose we have the limit as x approaches 1 of, let's say, x to the 5th plus x. Oh, I don't want to do that. Sorry, I was just writing this from the book, but the book has it's not a very nice example in the book. So let's just say we have the limit as x approaches 1, and let's say we have x times x minus 1 divided by x squared minus 1. And so if we were to rewrite this, right, we have the limit as x approaches 1 of, let's put a 3 there, of 3x squared minus 3x, sorry about that, divided by x squared minus 1. I'm kind of making up the example as I go. So notice if you plug in 1, right, you get 0 divided by 0. Normally you would factor both numerator and denominator and cancel the x minus 1s, but we don't need to do that. We can use L'Hopital's rule. L'Hopital's rule says that this limit will be the limit as x approaches 1 of the derivative of the top divided by the derivative of the bottom. So the derivative of the top will be 6x minus 3. Derivative of the bottom is 2x. Good. And now when you plug in 1, right, do you see that you don't get the problem anymore with 0 divided by 0? So now that's going to be 6 minus 3 divided by 2, or 3/2. Good. Now, what was the other way to do this? We said you would take 3x times x minus 1 divided by, and then you'd factor this, right, and then you'd just cancel the x minus 1s, and then you'd plug in 1, then you'd get 3 divided by 2 that way, and so that's how you get the 3/2. Okay, So in this case, we just have to check that we have 0 over 0 or infinity over infinity, and then we can take derivative divided by derivative. Good. Let's try another example. How about the limit as x approaches 1 again, but this time it's going to be the natural log of x divided by x minus 1. And let's see what we get. So let's see, the natural log of 1 is 0. Whoops, I'm running off the page. So that's 0 divided by 0, and so we can use L'Hopital's rule, and so therefore it's the limit as x approaches 1 of the derivative of the top divided by the derivative of the bottom. Derivative of the natural log of x we learned was 1 over x. Derivative of the bottom is just 1, and so now we see that the limit is 1. Easy. Let's see, maybe a couple more examples. So how would we compute the limit? Oops, I'm off the page again. As x approaches infinity of e to the x divided by x squared. Well, let's see. We can use L'Hopital's rule because we have infinity over infinity, and so we have the limit as x approaches infinity. Derivative of e to the x is e to the x. Derivative of x squared is 2x. And again, we have infinity divided by infinity, so we can use L'Hopital's rule again. And then we have e to the x divided by 2. And now, oops, I'm going off the page again. Sorry about that. And so now we can say, what is the limit then as x approaches infinity? Now we don't have infinity over infinity, but we do have just infinity, right? E to the x just goes to infinity, and so this ends up being infinity, and that is okay. We said at the beginning, right on the other page, that L'Hopital's rule was valid provided the limit exists or the limit is plus or minus infinity. So in this case, we had the plus or minus infinity. Good, and so we had no problems with L'Hopital's rule. Good. How about just finding another example. Let me pause for a second to find a good example. Okay, so this is exercise 3 in the exercise section for 2.8. And so let's take a look at the limit as x approaches 0 of 1 minus cosine of 7x divided by 1 minus cosine of 3x. And we notice, right, that if you plug in 0, cosine of 0 is 1, so this would be 1 minus 1 and 1 minus 1. So you do have 0 over 0. And so far, we will try to apply L'Hopital and see what we get. So derivative of cosine is minus the sine, that's 0, right? So that's going to be a positive sine of 7x times the derivative of 7x is 7. And down here, we'll have 0 plus the sine of 3x. And so that'll be the sine of 3x. Good. Times, now this the 3x comes out as 3. Good. Now when I take the limit as x approaches 0, I do have 0 divided by 0, right? So I can't do that, or I can apply L'Hopital one more time and see what happens. Derivative of the sine is cosine. And then I'll have cosine of 7x times another 7, so that'll be 49, divided by cosine of 3x times 3 squared, which is 9. Good. And now when I put in x equals 0, I get cosine of 0 and cosine of 0, which is 1 and 1, so that's going to be 49 over 9. Good. Alright, so let's try just a little quick example here. Maybe we're backing up to do some polynomial over polynomial problems. So how about an example? Q of x is equal to 3x squared minus 4x plus 5 divided by 7x squared plus 9x minus 10. Okay, and we're asked to see what happens as x goes to infinity. q of x do. And so we're taking the limit as x goes to infinity of our 3x squared minus 4x plus 5 divided by 7x squared plus 9x minus 10. Good. Now, one way to think about it is as x gets really, really big, these constant terms are going to become meaningless. You know, if you're dealing with x in the millions, right, a 5 and a 10 is not going to matter at all. Similarly, x squared is going to be much, much bigger than x. And so you can think of the 3x squared is like the dominating term of the numerator, and the 7x squared is going to be the dominating term of the denominator. And so one way to do the analysis here is just intuitively and say that intuitively this should behave much like the limit as x goes to infinity of just 3x squared divided by 7x squared, and then the x squared is cancelled and you're left with 3/7. Okay, now this is intuitive, right? We're just saying take dominating term divided by dominating term. This is the section on L'Hopital's rule, and so we can apply L'Hopital in this section. So let's just see what happens when we do apply L'Hopital. Okay, so we'll just say we'll abbreviate that L'Hopital's rule with that L. That's going to be the limit as x goes to infinity. So this is infinity over infinity, and so we get 6x minus 4 divided by 14x plus 9. Okay, so again, going to infinity, we still have infinity over infinity, and so that's just going to be 16 over, or 6 over 14, right? Derivative divided by derivative. Good. And of course that is equal to divide top and bottom by 2, and we get 3 over 7. Good. Oops, let me find another good example. Alright, here's another example. We have the limit as x goes to infinity of the natural log of the square root of x divided by x squared. Now, as x goes to infinity, right, the square root function also goes to infinity, and the natural log of something that's growing to infinity also goes to infinity. So the numerator does go to infinity, and then the denominator x squared also goes to infinity as x gets big. So this is the case where we have the infinity over infinity situation, and so that is a valid setup for L'Hopital. And so now we use L'Hopital. L'Hopital, and so we take the derivative of the top divided by the derivative of the bottom. So the derivative of the top, I'm going to go ahead and write that as x to the 1/2 power. So what's the derivative of the natural log of something? It's 1 over that something, so this is going to be 1 over x to the 1/2 power, right, times the derivative of x to the 1/2 power. Oops, I'm running off the top of the page again, sorry about that. So that's going to be the derivative of the square root, and that's going to be 1/2 x to the minus 1/2, right? So that's all in the numerator, divided by the derivative of the denominator, which is just 2x. Alright, let's see. Let's simplify things before we take any more limits. We'll just say limit as x goes to infinity there. So the 2 goes in the denominator, and the x to the 1/2 goes in the denominator. Square root of x times square root of x is just going to be x for x positive. So this is going to be 1 over 2x divided by 2x actually over 1. And so, right, because this is always over 1. And so now, that's not L'Hopital here. This is just algebra, right? And so, what does that simplify to? 1 over 2x times 2x over 1, and 1 over 2x is 1 over 2x. That's 4x squared. Good. Now, if we take the limit as x goes to infinity of this, right, the denominator is growing without bound, and so your fraction overall is going to 0, right? So it'd be something like 1 over 100, 1 over 1,000, 1 over 10,000, right? So here the denominator is getting huge, but the numerator is not. And so overall this is going to 0. And so this limit is equal to 0. Very good.